Hi, everyone. I'm going to introduce to you the basics about Bayesian decision theory. The slides are a courtesy of Dr. Mustafa's lecture slides from Caltech University, and our goal here is to get a feel of this concept. Some of the most robust machine learning approaches, however, guys, are actually based on Bayesian decision making. And more surprisingly, it is a very intuitive approach. So intuitive that after you've seen it for the first time, you would think to yourself probably that, oh, I've been using this approach all along in my decision making, in my everyday decision makings. So some basics first. Let's introduce some notations and notions of probabilities. Let's introduce these concepts in the context of protein mass spectrometry, which is a process that of finding out, identifying a protein based on measures from a mass to charge ratio of its charged particles. The basics, the details about the mass spec machine is not important. What is important is that I have a machine, it outputs a singular score, and based on that score, I have two possibilities. Either the score represents a known protein or an unknown protein, or maybe even noise or an unknown peptide. That would be my variable y. So the question here is, if I'm observing a particular score, what is the likelihood of it being a known protein? What that means is that, let's say we have this machine and we use it for a year, and we kind of observe different values of about the scores. So you have varying values depending on if a known protein was used or not, and other aspects which we're not aware of in the machine. Maybe there's inherent noise, maybe there's other things, but we see a trend of scores. And we might see score of 10, for example, much more frequently than a score of 100. Because score of 100 is more rare to occur. That's when you have an exact known protein, for example. That would be my P of X. It would look like a function over all possibilities of X, and it would tell me basically the expected frequency of a particular score if I look at that graph. What is P of Y given X? Well, this is kind of one of the things that we are after, actually. It is the likelihood, as I highlighted here, of observing Y given X. So for example, if I'm observing a score of 10, now this is my observation now, X is not a random variable anymore. I actually know what it is. That's why I write it on the other side of the line. And this is a conditional probability notation. So if I'm observing X, what is the likelihood for Y to be +1? And Y is also a random variable. It can either be +1 or -1. P of Y given X multiplied by P of X is kind of related to the joint probability distribution. It's not something that we are immediately concerned with right now. But we basically, what we want to do is to come up with a way of making decisions so that most of the times I am predicting the correct value for Y. This is our goal. So if you look at it the other way around, I make mistakes in my prediction when my prediction of Y does not match the actual ground truth. That would be f of X. So X is a given score. Let's say X is a score we observe. I have an H of X, which is basically my strategy about when I observe X. That would be H of X. And this basically can, for example, one possibility of this would be if I have a threshold, for example. So if, let's say, my threshold is 15. If I see anything less than 15, I assign -1. And if I see anything higher than 15, I assign +1. I would say, oh, that's a known protein. That's my strategy. That's my decision boundary, basically, the 15. And h of x is how we symbolize that. So given x equal to 10, h of x, for my case, would be -1 because it's less than 15 for this hypothetical scenario that I explained to you. So basically, the error would then be, when would I make a mistake? Well, if I'm observing a score of 10, let's just stick to 10, for example, and a threshold of 15. If I'm observing a score of 10, it may be that y is -1. So in those cases, I'm making a correct classification. But there may be times that the protein is actually known, y is +1, but the score is still 10. Those times, those portion of times, I'm making a mistake. I'm doing a misclassification. So that would be my error for that particular score. That would be my average error. So in other words, let's say I'm observing a score of 10. I'm observing a lot of scores in my machine that I'm using. Let's just look at scores of 10. It's maybe 200 times I observed exactly score of 10. And out of those 200 times, it turns out that 20% of the times, it was actually related to a known protein. And I'm misclassifying it as unknown. So P of y equal 1, given x would be 0.2. My error would be 20% for that particular x. You don't even have to worry about the second term, because for a fixed x of 10 and a fixed threshold of 15, I'm always making a decision of -1. So my error is 0.2. Okay, so I know how to get the error of my mass spec if I know for a particular score. So that's great. Well, all I need then is just these two terms. To calculate the error, I need my threshold, basically h of x, which is what I have. That's what I'm deciding. It's 15. That's h of x. I need to know what my strategy of classification is. That's h of x. I also need to have p of y given x. I need to know those times that the machine is making a mistake or not, given a particular score. I need to have that. So I'm not telling you now, I'm not telling you yet how to get this. We'll get here, we'll get to this point. But for the sake of this part, if you do have P of y given x, and you do have h of x, you can come up with a representation of the error. What I'm more interested in is not the representation of error only for a particular value of x, but over all possibilities of x, of course. And basically, so let's say if I'm observing, I'm using my mass spec machine for a year and I have different values of x and I'm making predictions. Overall, I want to know over a past period of time, let's say a year, how many times I made a mistake. So I have to take into account all possibilities of x's. The previous slide was just representing an error of a particular x, a fixed x, and a fixed threshold. Now I have a fixed threshold. H of x is always, let's say, 15, but my x could be anything. One day I'm observing x of a score of 10, another day is 1,000, the other day is -20. So basically, I have to average the error corresponding to each value, each score, over all possibilities of scores. And basically, that would be my average error. Except we should add actually one more thing. You can imagine in a year, you might be dealing with the scores of around 20 or 20 to 30, much more than scores of 2,000, which is very rare. So when I'm talking about an average error, I better weigh these errors by the frequency that they actually occur. And that is nothing other than expectation. I would actually have to, in this case, we call this expectation of the error, which is nothing other than weighted average. And those weights are actually probabilities of a particular score, as you can see here. So I'm averaging this in the integration. I'm averaging over all possibilities of errors and weigh them by the frequency that they happen. That's P of X. So when we have a known values and we want to take average of them, that's one thing. But if we have a random variable that can take different values with different likelihoods, that's another thing. In that case, in the latter case, we call that weighted average expectation, because it is defined over a random variable. Okay, so it came down to a point of minimizing basically the expectation of the error. I have to come up with a strategy. Basically, I have to come up with finding a way to actually identify that best threshold over which my average error is minimal. So if I have only one choice. Let's say I stick to threshold 15. So over a year, would I have minimum number of misclassifications than if my threshold was, let's say, 200? The classification problem is now finding that threshold. So I'm minimizing the out of sample error. I have, again, I have a strategy H that I have to find that best H that minimizes this error, this out of sample error. And I have a distribution, conditional distribution probabilities. Again, I'm not telling you how to calculate these yet. We have no idea how to get this P of Y given X. We just know that if we had it, it would be great, because I know the likelihood of known proteins or unknown proteins if I'm observing a particular score. If I have all those likelihoods, that would be really great. What Bayesian decision theory says is that if you do have the probability distributions, what I'm highlighting here, you should choose your threshold or your decision boundary in such a way that for any X, for any score, it should assign +1 to Y if the likelihood of Y being equal to +1 is higher than Y being equal to -1. I mean, that sounded super intuitive, basically. I mean, there is no other way, basically, to find the threshold, right? If the likelihood of +1 is higher, I should assign my prediction as +1. That's just very logical. Again, I have to have these conditional probabilities. But if I do, the Bayesian theorem actually dictates that if I find my threshold and which actually satisfies this equation, that will guarantee the lowest possible error over time. So anyone else comes and says, oh, I have another threshold that works better. That is not true. If you have the conditional probability distributions, that dictates basically the best decision, what it is. And that's the Bayesian decision. And it is optimum. The expected error would be minimum. Okay, so let's just do a little review. So we had two random variables in our context. One was X. X was just a score. I could take it was a continuous scalar variable where it could take on any values. And then we had Y. Y was a random variable, but Y could only be +1 or -1. +1 would indicate a known protein, -1 would indicate false or unknown protein. Okay, so we have X, we have Y. So we probably have four notions that we have to deal with. So P of X, P of Y, P of Y given X, and P of X given Y. So what are these? Well, first of all, we know P of X. We talked about it. P of X is the frequency of X, the distribution of the random variable X. So for example, P of X would, we already talked about P of X, is just the probability distribution of the scores. So over a past, let's say a period of time, let's say a past year, I'm observing my scores. I don't care if it's a known protein or not, but I'm observing my scores of X's, and I see the frequency of score X being equal to 10 is, let's say, very high. It's, let's say, I don't know, 80%. And the 20% of the times X was some other value. That would give me P of X. I have an idea of an expectation of X. So I know that a score 20 is more likely to occur no matter what Y is. That would be P of X. P of Y is a little more tricky. P of probability of Y is the likelihood of a known protein. So let's say over that period of year, if I use, let's say, my mass spec machine 1,000 times, and 20% of those times, 200 times of those, it was actually a known protein that was sequenced, a protein that was known to the database and to my mass spec machine. 20% of the times, Y was +1, and 80% of the times, Y was -1. Let's say I know that for the past year. For the next year, when I'm using the machine, even without observing X, even without even observing a score, my expectation is that, okay, probably 80%, with the 80% chance, I'm dealing with an unknown protein because I know from last year, that's my expectation. That is P of Y. So what is P of Y given X? Well, this is actually, again, what we are after. That is the likelihood of a known protein being sequenced given a particular score. Now I observe my score. I observe a score of, let's say, 200. The likelihood of Y being +1 is much higher than observing a score of 5 and comparing that to the likelihood of a known protein. Okay, so now we know P of X, P of Y, P of Y given X. So what is P of X given Y? Well, P of X given Y is, and you can kind of see that here, just ignore the +1, P of X given Y. This is actually the likelihood of observing the score if I knew about my protein. If, for example, if I knew that I'm using a known protein, if I knew that if Y is +1, then what are the scores that I expect to see? And, you know, surprisingly, P of X given Y, which we haven't talked about yet, is actually the one that we can easily compute. All I need to do, for example, for a month, in order to actually compute this value for a month, I would just give known proteins to my mass spec machine and observe the scores I get. So Y would be always +1, and I would probably get a possibilities of the scores. I would probably get a high scores, but it would vary. It wouldn't always be a particular number. It would have a distribution. And I can do the same thing when Y is -1. I would, let's say, feed in noise or unknown peptides, basically something corresponding to Y equal -1. And I would just record the scores that are the output of my machine. So I can actually calculate P of X given Y. So we have, in a real world scenario, we have P of X. We have P of Y. We also have P of X given Y for any X or any Y. X is a continuous value, scalar variable, and Y is just binary. It could be +1 or -1, but we do have those. So what Bayesian theorem does is that it can tell us what is P of Y given X. It can reformulate that based on the other three expressions. So the fourth one, which is what we're after, And again, just ignore the plus ones here. Just think of this as P of Y given X. P of Y given X, according to Bayesian theorem, is nothing other than P of X given Y multiplied by P of Y, prior probability, divided by P of X. And I haven't written P of X here. This is P of X in terms of, again, conditional probability distributions. Let's not worry about this right now. But what Bayesian theorem does is that it represents your conditional probability, what we are after, in terms of the things we can calculate. And this, guys, varies with different, it's not just for a mass spec, it varies from question to question, but it's always kind of in the same structure where you want to know the likelihood of a variable given your observation, your observed data X. And Bayesian theorem kind of reformulates it in a kind of in a reverse chronological sense, where you would actually can calculate this value based on P of X given Y. And that's Bayesian theorem, basically. So from here on, it's just a matter of plugging in numbers and kind of understanding boundaries and getting a feel of these equations and how they kind of affect your decision. But basically, it all comes down to this. The P of Y given X equals P of X given Y multiplied by P of Y divided by P of X. We do this on a regular basis, guys. This is not just for this particular example. Let's say this is something that we do when we make decisions even every day. Let's say I'm driving down a street and I see a lot of traffic. So my observation X here is the high traffic patterns maybe. And Y would be, let's say, I'm thinking to myself, has there an accident occurred? So I don't know the likelihood of an accident, but I do see my observation of high traffic. So what I do intuitively, and we do this so naturally, is that we would think to ourselves, well, if there was an accident, you see, I'm kind of reversing the chronology. If there was an accident, let's say if Y was +1, what would be the likelihood of seeing these many cars? And let's say we would kind of assume an alternative scenario where maybe if there was no accident, but maybe there was a police stopping someone for giving them a ticket, what would be the likelihood of seeing this type of traffic again? So you see, I am doing Bayesian theorem. I just don't call it Bayesian. I am assuming two possibilities, and I want to see what is the likelihood of what I observe right now. So that is basically how we kind of organize our probabilities and make a decision. Basically, that's how we take a posterior probability distribution and define it in terms of prior distribution and conditional distributions of X. Again, if you remember, according to the previous slides, the way I need now, let's go back to our original question. We had to find a threshold. Basically, we had to find H of X. We had to find a strategy of assigning +1 and -1s to the observed scores that I get. Okay, so basically, we learned that according to Bayesian theorem, if the probability of Y equals 1 is higher than probability of Y equals -1, given a particular score, observed score, then I should always go with the one with the higher probability. That was just logical, and that's just another way of reiterating Bayesian theorem. Now, the good news is, well, this is something we already knew, but the good news is that I can actually compute these guys in terms of the above equations. So P of Y equals 1 given X is proportional to P of X given Y multiplied by P of Y. And you see we kind of dropped the denominator here because it doesn't affect our decision-making process. This is always a constant value, no matter if y is +1 or -1. You're always adding these two. So this always is the same value. It could be 0.2 plus 0.8, for example, for both cases. So we don't care about this. We just care about this part. We use this part instead of this part. And the representation of it is that, what this means in terms of values of scores is that if you look here, P of X given Y is actually the likelihood of seeing a score upon knowing Y. So if these are my scores, the horizontal, and if I know that I am feeding the machine a known protein, I know that, then let's say if I'm giving a machine known proteins, I'll probably see higher score. So I see these color line, as you can see, it's kind of the greenish color line here. I see that guy. So for example, this set might be centered around a higher score because I'm giving it known proteins. I can get this curve actually by just doing experiments and recording X's. And then I have another curve for Y equal -1 that I'm giving, let's say, unknown proteins, and I get a lower score. And if you look here, you kind of can see how these two graphs connect in terms of the logic of P of Y given X. So the first one is P of X given Y. Let's forget about this other term. The other graph is P of Y given X. So that's the likelihood of Y being equal to +1, for example, given an observed X. You can see this kind of increasing. The green is increasing. This is for +1. That's because as my score increases, the value of P of X given Y divided by P of X given Y equals +1 divided by P of that particular X given Y equals -1 is much higher. It increases if I divide these guys. So if this is much higher than this, I better make a decision that it is Y +1 that's happening. So that's why you see this curve increasing. This is nothing other than just dividing these two curves together, basically. And to rearrange these terms, and we can actually rearrange these terms, divide conditional probabilities by each other, and we can kind of represent this decision-making criteria in a different form. It's just dividing them, and we can take the log of these expressions. Log is something that is kind of convenient numerically and also mathematically, but it doesn't really interfere with our decision-making process. It's a easier. It kind of makes life easy for mathematicians, basically. But the whole idea is basically that I am dividing two values of P of X for alternative values of Y, and if it's higher than a threshold, I will make a decision that about Y. So basically, you see, this equation implies that if I divide this term by this term, and if that's higher than a threshold, then I should always assign +1 to Y, basically. And that kind of corresponds to for a particular score, for this particular line, dividing the value on this curve by the value of this curve. As you can see, if I go forward, if I increase the score, I guess it becomes more deterministic that, oh, I'm probably dealing with Y +1. It's probably a known protein if I have a very high score, because the likelihood for this guy kind of dies. And if I go the other way around, of course, I can do vice versa. The problem is in the center where you have both possibilities. And let me reiterate, there is no way to avoid error altogether. No matter what threshold you choose, there is a portion of portion of experiments that will be misclassified. There is no win. What we're doing in Bayesian is actually minimizing these errors, and that could be equivalent to kind of putting our decision boundary where these two curves of P of X given Y's would actually meet right here. And in a real example, in a real world situation, let's say I actually have the values of Y's. I have prior probabilities. Y being equal to 1 is 0.25. Minus 1 is, of course, 0.75. I have the overall likelihoods. Let's say these are a known protein and an unknown protein, for example. The probability of them being used in my machine, regardless of what score I get. That's just the frequency of them. And then let's say I have the likelihood functions. I have P of X given Y in form of a normal distribution. So in this particular example, I do have the likelihood functions of P of X given Y. What does this mean? Again, if you remember, if Y equals 1, that means my protein is known. So if the protein is known, and I feed it to the machine, I probably get a high score. So basically what I will get is this curve, as labeled as true. I will see this curve that I see my scores centered around a high value. That would be the mean of it. I would not always get a particular score, but I would get a distribution of high scores. That can be represented by normal distribution. If you see this equation, guys, this equation is actually it's in terms of X, first of all, which is the score. And it's kind of, if you draw this equation, it is kind of a curve, a bell-shaped curve, it is centered around this value 15, what is in the exponent. So this equation corresponds to this curve, and this guy is 15. And this other equation is 5. It is centered around 5. So that's a normal distribution. That's kind of just telling us this is the distribution of the scores. We can actually, as I said, we can actually calculate this by just recording values corresponding to known proteins. And some people take it one step further, and they actually do interpolation, and they come up with an analytic equation, and all of a sudden they come up with a normal, let's say, a distribution function that can kind of analytically be used. But the basis of this is again those experiments. Either way, we have P of X given Y for +1 and -1. We have P of Y for +1 and -1, and this is all I need to come up with the best threshold that will give me minimum error according to the Bayesian theorem. It will give me minimum error and minimum misclassification of Y given my observed scores of X. So if you notice here, we have P of Y, we have P of X given Y, and we also have P of X. P of X is also dependent on these guys. It's basically defined. If you go in the previous slide, that's the denominator. It's actually defined based on these. So all I need is these 4 expressions. And just plugging in the numbers, I can actually, basically what I need to do, again, to reiterate, is to find a threshold in H of X that assigns +1 whenever probability of +1 over is higher than probability of -1 for any X, for an observed X. Plugging the values, first we calculate our constant value, and then we divide the distributions, and this is just reorganizing the terms. This is nothing surprising. I'm basically dividing these terms. I'm taking the log of them. Now you can see why log likelihood is kind of useful, because it kind of makes life easy in terms of simplifying these complicated equations with a couple of simplifications. I actually will get this final value. My decision boundary would basically, of course, be in terms of X. and it is a threshold. If X is larger than a specific threshold, I should assign +1. And if it's lower, I should assign -1. And that threshold in our particular example is 10.1. What this means is that if I observe a score of higher than 10.1, I should always classify the protein as known. I should always settle for Y equal to 1. And if I observe my score to be less than 10.1, I should always predict Y to be -1. If I go according to this strategy, and if I make decisions this way, then over a span of time, let's say in a year, in the next year, if I make decisions this way, my overall misclassification will be less than any other choice of threshold. Anyone else comes and says, oh, I have another threshold that works better, it's just not true. This is what Bayesian theorem guarantees. And if you can see, it kind of depicts in terms of probability distributions. What happens here is that P of X given Y multiplied by P of Y is actually looks like a kind of a normal distribution that's kind of inflated. So I have two curves because Y can be +1 or -1. One curve is when Y is -1. One curve is Y when Y is +1. And what the decision boundary is when those curves actually meet, when they're equal together. That's the 10.1 value here. Intuitively speaking, guys, as you can see, if the likelihood of P of Y -1 is much higher, this curve goes up, it becomes actually greater, and it kind of pushes the boundary, as you can see, to the right. What this really means intuitively is, if I have all these likelihood probability distributions, but if for a year I'm observing, and most of the times I'm not seeing known proteins. Let's say I do these experiments for 1 year, and I don't see a lot of known proteins. 95% of the times I'm dealing with unknown proteins. So next year, in order to make decisions, I kind of can incorporate that. I can, if I'm observing a score, I will still give chance for it to be an unknown protein, because was my prior